So I'm going to be talking about my project. So I'm a third-year PhD student at the University of Southampton, and I've been working on a project which is looking at producing continuous gravitational waves from what are called thermal mountains from magnetized neutron stars. And so to begin with, so looking at continuous gravitational waves, very different from what LIGO, Virgo Cagra has already observed from transient signals, so binary in-spirals. So for continuous waves, one of the most promising sources are from these low mass X-ray binaries. So these are neutron stars that have a sort of one solar mass-ish companion that orbits it, and from which it accretes matter from. And so you end up, so the neutron star would be at the very center of this black portion here, and you get an accretion disk as it pulls matter from the other star. And so these are very interesting objects because we observe most of them to be rotating sort of in the region 300 to 700 hertz. But this is very odd since as the star accretes, we think these systems are very old, millions of years old. And so as they continue to accrete, this adds like a spin-up torque. It adds angular momentum to the neutron star. And so if it accretes uninterrupted, you would think that it would just continually spinning up until it hits more towards what's called the breakup frequency at about 1000 to 1500 hertz. But clearly we don't see this. And so logically it implies that there's something getting in the way. And so a guy, Lars Bilston, came along who suggested that the angular momentum from the accretion might actually be lost due to gravitational wave radiation. And so the star continues to accrete until it hits some particular frequency, at which point some gravitational wave radiation sets in, and then you reach what's called the torque balance. And so obviously the next question after that is where does the gravitational wave emission come from in the first place? And so what Bilston suggested was that there could be some kind of large-scale asymmetry in the temperature profile of the star, which importantly must be misaligned from the spin axis. And so moving on to what Bilston termed the wavy capture layer, the structure of accreting neutron stars are quite different from their isolated counterparts, and you sort of get this onion-like structure. And so on the surface, we have some hydrogen and helium. If I just flick back to this diagram here, hydrogen and helium is mostly what's accreted from the companion, and that settles on the surface, at which point it ignites. And basically, you get things like the RP process going on, and you build up heavier and heavier elements until you reach iron 56, which is quite a stable element of iron, isotope of iron, sorry. And so that's where the burning stops. But whilst this is all going on, you're continually getting fresh matter accreted over from the companion. And so eventually that iron, we think, sinks down into the surface of the neutron star. And so it begins to sink down until it reaches some particular density where it can capture a free electron that's just somewhere within the crust of the star. And so a proton is converted to a neutron, and we get some chromium-56 forming. And then again, as more and more matter is funneled onto the star, that chromium then gets pushed down until it captures an electron, becoming titanium, and so on until you reach the center of the star. And so that's what this, on the right-hand side, that's what this dashed line indicates here. It's these lines of constant composition of particular elements. And so these are predominantly density-dependent reactions that you need to be a dense enough point in order for the electron captures to occur. But what Bilston showed was that they also have some slight temperature dependence as well. And so what that means is if you do have some kind of temperature gradient going on within the crust of the star, at some locally hotter region, you can get electron captures that are going on at a lower density, so higher up in the star, than a colder region on the right. Sorry if I just get this out of the way. So on a colder region on the right, it occurs at high density, and in a hotter region, it can occur at lower density. And so this is effectively the wavy capture layer. And so the important thing for gravitational wave emission is that the mass distribution is also going to be affected. So by changing the location of the capture layer, at different portions in the star, you're getting a non-axisymmetric mass distribution. And so obviously the question after that, which was never really answered, is what would actually introduce this temperature asymmetry in the first place? And so the idea that we're exploring and that we've sort of devised is that a magnetic field might be responsible for introducing some kind of asymmetry in the temperature profile. And the reason for that is that we know that it's relativistic electrons that are the primary carriers of heat in the neutron star. And so in an unmagnetized star, the electrons would just be free to move around and the heat is just conducted sort of amorphously around the star. But if we then bring in a magnetic field, the electrons are of course going to be forced to follow the field lines. And so they're sort of restricted into certain configurations within the star. And so what happens is that this makes the thermal conductivity anisotropic. So just from basic Fourier's law, we have some heat flux F, which is proportional to the gradient of the temperature, along with the thermal conductivity, which is essentially the constant of proportionality. And so the important thing is that when you introduce the magnetic field, the thermal conductivity, essentially the heat gets suppressed in directions perpendicular to the magnetic field. It's sort of in contrast to the parallel component of the conductivity. And so this is what is sort of written here. So we have the amount of anisotropy, so that the ratio of the parallel and perpendicular pieces of the conductivity is given by this, what we call the magnetization parameter, this omega b tau. So tau just encodes what we call the scattering frequencies, so how efficiently the heat is being pushed around by the electrons, and this omega b, which is the gyromagnetic frequency, which encodes the strength of the magnetic field. And so basically this idea is used a lot when it comes to magnetars. So they're in the regime where omega b tau is much greater than 1, and so you get a large amount of anisotropy. But the important thing with these LMXBs is that the expected strength of the magnetic field is much lower than that. It's sort of 10 to the 8, 10 to the 9 Gauss, so orders of magnitude smaller than you'd find around a magnetar. And so what we can do is actually treat the anisotropy introduced from the magnetic field as a perturbation. So sorry, we introduce the magnetic field as a perturbation on the heat flow. And so I've left out the sort of the nitty-gritty details of the mathematics that goes into this, but what you can do is you decompose, so you would end up with some temperature variation from the magnetic field, and we write it down in terms of the spherical harmonics. So we have a radial piece that we can solve for, and then we have this YLM piece for the polar and axial part. And because we're interested in gravitational wave emission and the mass quadrupole, we specify to the L equals M equals 2 portion. And what we end up with when we bring in the magnetic field are these regions, these hot and cold spots.
Yeah, that's your 2-minute warning, Thomas.
Yeah, thank you. So in the red region is a hotter portion of the star, and obviously in the blue it's colder. And so if we imagine that the star is spinning around the z-axis, then on the right-hand side, if I go back to the plot that I had before, the little cartoon description, in the XY plane, this is essentially what we have going on. So in a red region, we have a location where it's hotter, and so the electron captures can happen at the lower density, and over here in a cold spot where the electron captures have to happen at a denser portion. And so this really is just a visual description of what the neutron star, it would be deformed into this shape essentially. And so as it spins, you would get some sort of gravitational wave emission from that. And then, so I think I finished a tiny bit early, but just to summarize, we think that neutron stars in these LMXB systems may have their spins just limited by gravitational waves until they reach what we call the torque balance. And that's because some kind of asymmetry in the interior temperature profile can sort of form a non-axisymmetric mass distribution within the star. And that is determined by the strength of the magnetic field in terms of this magnetization parameter. And the last thing, sorry, I didn't say on the previous slide was that it's been inferred that you need sort of about a % level asymmetry in order to produce a mountain that would be significantly large enough in order to produce gravitational waves that we might hope to detect in the future as the Einstein telescope era and beyond.
All right, thank you very much, Thomas. That was great. We have one question in the chat, which is what kind of configuration do you choose for the magnetic field? Do you allow for its evolution?
So no, so this is only a static solution for one, but it's very interesting, and I didn't have time to go into the details, but essentially it's only the toroidal component of the magnetic field. So once you decompose it into its poloidal and toroidal parts, you find only the toroidal part that affects it. And then in our calculations, we just assume a simple quartic expression for the magnitude of the field at each point in the star. It's essentially how the calculation goes.
Okay, thank you very much. There is one more question. I guess we can squeeze in just this last quick question from Greg, because I've already cut him off once. He asks, what frequency are the gravitational waves emitted in this mechanism?
So there'd be twice the spin frequency is what you would think. Just essentially that. So you would reach torque balance at some particular rotational frequency, and then the gravitational waves would just be twice that.
Okay, brilliant. Thank you very much, Thomas. That was great, and thank you to all the speakers in this session. There's some really interesting talks there. I'm not sure if there's any announcements before lunch that were going to be made. If not, then I think we start again at 1:30. So I'll see you all after the break. Thank you.